is in fact the distributed load. Okay. So now some of you might say, what are we doing down here? Okay. So there are two loading condition. Okay. In the two commonly loading condition that we can represent with equivalent load. Okay, I'm going to do a side lecture over here. Okay, I think you guys have seen this, but I want you to recap. Okay, what do I mean by that? Okay, so there's two types of distributed load. So one is uniformly. Let me be in a mode with the table. Hold on. So this is the uniformly distributed load. Okay. So let's say if our beam, we have a beam. Okay, we have a beam over here. Okay, and the length is simply supported. So we have a uniformly distributed load. Uniformly means throughout the whole length, the load is uniform. Right? And the distance from here to here is L. Okay. And the distributed load is omega, and the unit is Newton per meter. Okay. So mathematically, if you were to look at the distributed load trend, or diagram, right? If we have an axis over here, right? And then we have another axis over here. So this is X, and this is omega, right? So we have a load from here up to a certain length, okay? Up to the length down here, this is L, okay? So this is our omega magnitude, okay? So the equivalent load is the area under the line. So IE is this area over here, up to L. Okay. So when that's the case, right, your equivalent load will be equal to omega L, right? Length times breadth. Okay. And then when you construct your free body diagram, okay, when you construct your free body diagram, okay, so when you construct your free body diagram, right? So this is your I call this AY. This is your BY. So your equivalent load over here is omega L. And because it's evenly distributed, the distance from here to here is L over 2. And the distance from here to here is L over 2. Okay. Now, if we were to have a gradient distributed load, okay, right? This is straightforward, right? I believe this is straightforward, okay, for a uniformly distributed load. Now, for a gradient distributed load, I need more space. So next, we are going to look at a gradient distributed load. I think now you guys get it, why half base times height, right? So now again, this is our structure, right? This is our structure, and then our structure has a distributed load of a gradient. Okay, and this is what I call omega naught, for example. Now omega naught over here, right? Omega naught over here that you see is the highest magnitude of the longest arrow. Okay, is the highest magnitude of the longest what? Arrow. Okay, so when that's the case, again, this entire structure is simply supported. Okay, and again, same thing like the one before, is given the length L. Okay, so now we are again going to construct the load and distance diagram. Right, then we know that this is the load and displacement diagram. So this is X, this is omega, and up to here is your omega naught. And then area under the curve, right? So we have a distance L over here. So the equivalent load is equal to half multiplied by omega naught L. Okay, half base times height, because it's an area of a triangle. Now where is acting? Okay, so if we look at the free body diagram, right? So likewise, you have AY, you have BY. Okay, so where is acting? Right, so the equivalent now is no more in the center. Okay, is omega naught L over 2. The distance from here to here is L over 3, and the distance from here to here is 2L over 3. Okay, now next week I will explain to you why. Okay, I now, because I want to finish this example, then you can do your homework. Okay, let me finish this first. Next week I explain to you why. Okay, now if we have a load, now this load is rising from left to right. If it goes from right to left, okay, let's say same structure, right? So now it's doing this direction. Okay, now it's doing this direction. Let's say now this is your distributed load, this way now. Right, now this is your distributed load. Right, so this is still your omega naught. Okay, so when you construct your free body diagram, right, so this is your AY, BY. So now the load is over this side now. Okay, so this is half omega naught L. The distance from here to here now is L over 3, and the distance from here to here is 2L over 3. Okay, right? So now you can more or less understand how this, where is the, how to calculate the equivalent load, which is area under the line, right? And where the position of the equivalent load is acting. If it's evenly distributed load, it is L over 2, and if it's gradient, okay, depending on how the slope is it positive slope or negative slope, is L over 3 at one end and 2 L over 3 at the other. Okay, I think you guys have seen this before. It's just a matter of refreshing. Okay. So now you know how we got 2/3 over 6 times 4 and how we get 60 times 10 to the power 3 and 4 meter over here. Okay. So the next thing we're going to do, we are going to calculate. We are going to do static analysis. Okay, we're going to apply static analysis first. Okay, so after your free body diagram, we're going to apply static analysis. Okay. Now before we go on, right? The question did mention this. Okay, the question did mention that ABC or member ABC is a rigid body. Okay. Now, what do I mean by rigid body? Okay, and I'll explain to you. When they mean rigid body is during deformation. Okay, the structure will be linear. So what do we mean by that? Okay, so now I'm going to draw member ABC. Right, so member ABC. This is our member ABC. Okay, so this is our point A, point B, point C. Okay, so the next line I'm going to draw is a deformation pattern. Okay, so when it's loaded, because we assume it to be what? Rigid body, the deformation pattern is a straight line. Okay, so this is our point A, B prime, and this is our C prime, and this represent our or deflection or deflection is a better word. Deflection under loading. And because we assume a rigid body, okay, it is linear. Okay. So you ask me in real life how this, maybe in real life it will look like that. So in real life the deflection will or the beam will deflect this way. Okay, in real life. Okay, so this is real life. Okay. Okay, or real. Okay, no need put the real deflection. Okay, but we simplify our analysis. Okay, why we simplify analysis? Wait, you appreciate it. Okay, wait. So we know from the distance from here to here is our delta B, and we know the distance from here to here, this is our delta C. Okay, again we follow the transformation. This is X and Y, and this is our rotation about Z. Okay, so from here we want to find out. Okay, we want to find so let me write down the procedure of the solution. Okay, so we're going to apply static analysis. Okay, to see can we solve first. Okay, we're going to apply static analysis. Okay, we're going to apply static analysis first. Okay, so now back to our free body diagram. Okay, Now at point A, we have some reaction also at point A. I'm going to assume A is to be my AY.